Hi class, welcome back to our next section. We're going to start chapter 2. Chapter 2 is where we start to actually solve differential equations. So the first section that we're going to do in chapter 2, 2.1, we're actually going to not be doing any solving, but we're just going to look at what these look like graphically, right? So we're going to look at sort of the geometry of what's going on when we're looking at solutions, when we have IVPs, things like that, right? As we go through chapter 2, however, there's going to be several sections where the material we're going over is review, okay? Now, you may not remember it because it's from Calculus 2, but quite a bit of what we're going to go over are things that show up in a standard Calculus 2 course in this section. So I would like to say that there is probably 3 sections out of the six in this chapter that are review style material. However, I find students still have problems with them because it's been a long time. Diffie Qs are not very intuitive. So it takes a while for people to get used to what's going on here. So when we go through them, we'll go through them pretty thoroughly, but a majority of what's going on in this section, or in this chapter, I'm sorry, is considered review material for this course, right? So let's go ahead and go into 2.1, which is solution curves without a solution. So here we are not going to have an explicit or even implicit solution available. Okay, so a lot of times we can't even find a solution. Okay, we have methods for how to approximate solutions, which is actually probably the most likely thing that's going to happen when you're solving these things in real world applications, like if you're building bridges and buildings and things like that. However, we can always look at what a potential solution curve would look like, okay, if we have a differential equation. So that's what we're going to talk about, is how to look at and analyze these solution curves without having an actual solution. So again, right, there may be times when we won't be able to find an explicit form of a solution, or even in an implicit form. In these cases, we can use the graphs to analyze the system and any of its potential solutions, or we would use numerical methods to create approximate solutions. So we covered this in quite a bit of detail in chapter 9, and we see a little bit of introduction to the numerical methods in 2.6, right? So we spent a lot of time on the numerical methods in chapter 9 in this textbook. Okay, so what we do is we use what's called direction fields, right? So you should be semi-familiar with this as well, also called slope fields. And a slope field is basically like a blanket of vectors where all of the vectors are the tangent lines to any potential solution at any given point, right? So you're looking at the XY Cartesian coordinate system, and at every single point in that Cartesian system, you draw a vector that represents the slope at that point. Okay, so we'll play around with a couple of little slope field generators here, and we'll see that we can kind of manipulate what we're able to use. But basically what this does is it allows us to basically create a direction field, right? A slope field, by looking at a point XY and plugging that into our differential equation, right? So when we plug whatever point we're interested in into our DE, we should get out the slope at that point. And again, what this does is it basically creates a plot of flow, right? So it looks kind of like a river where we can see where the flow would go, right? So what I generally tell students is, imagine that you were at a stream or a river, and it was full of ping pong balls, and you could see where everything is going. That's kind of what we're looking at, right? But we're using arrows to represent the same thing, and we can start to look at what our solutions will look like at a given initial point if we were to drop a particle into our stream at that point and follow where the direction takes us. That's how I think about it myself, right? So we can call this a flow map that helps us model the solution curve that passes through our specific choice of an initial condition, x naught, y naught, for our system. Now, making these by hand, practically impossible. And I'm not going to say it's impossible, but I mean, you could literally sit there for hours trying to create a direction field by hand. So you definitely want to use technology on questions like this where you're trying to create a direction field, right? So let's go ahead and do an example. Let's consider the equation y prime is x times 2 minus y, right? So again, this is dy dx, or we're going to use the y prime. Again, I said we're going to go back and forth through our notation. So if I want to create a direction field here, I'm just going to choose several points throughout my Cartesian coordinate system, plug them in, and find the slope or the rate of change at that point. Okay, so looking at a couple points, easy point here, 0, 1. Obviously, that's just going to give me 0 because it doesn't even matter what plugs into here because I'm multiplying it by 0 on the outside. So plugging that in gives me 0. So we would draw a short horizontal vector because if it's a slope of 0, again, right, that's a horizontal vector at 0, 1, since the rate of change here is 0. Okay, so f prime of this point gives me a 0, right? So this is called an equilibrium point because at this point I'm getting out 0, right? That's what it means to be in equilibrium, is that if the slope is 0 at that tangent line. So we also call an equilibrium point a critical point or a stability point. Okay, so it's very important. They are interchangeable. You will hear me say them, call them different things, right? One of the three throughout this lesson. All that basically means is that at that point you have a rate of change of 0, right? So just like when you're doing optimization problems, when we look for the critical points, the other names are equilibrium and stability points. Okay. If we look at the next point, 1, 1. Okay. We plug in 1 for x, 1 for y, and we're going to get out 1. So we would draw a slope with a 45-degree angle, right? Because that's what it means to have a rate of change of 1. It means you go up 1 over 1, right? So when I plug in 1, 2, it'll be the same thing. If I'm looking at y prime, we're going to get 1 times 2 minus 2, which is going to give me 0 as well. So that is also another equilibrium point, right? So we would do so over and over and over again over in the entire xy plane, or as much of the xy plane as we needed to look at to get some information. And we would basically get an image like this, right? So if you notice here, with an output of 2, right, everything is flat, okay? We get a flat line here, right? When we look at our input of 0, 1, you can't really see it, but this should also be a flat line. In fact, all over this line right here, we should have a flat line. However, we can't see it because of I don't have enough resolution, basically, right? I'm not showing all of my values. So that's how it works, right? So if x is 0, these should all be flat, which gives me a weird curve here. However, as I approach this, I have an asymptote there, right? So it's not real asymptote. It'll kind of go flat and come over, right? So you're getting more of like a curve at this kind of deal. But you can see here, I'm increasing very quickly. Here, I'm decreasing very quickly. So you can see these all kind of flow into this line. So if I were to, for instance, drop a ball into this, a ping pong ball into this flow, it would just flow in a straight line here. Okay. So we'll get into this later, but we call this an equilibrium line, right? A line of equilibrium, or an equilibrium solution, I should say, right? So it's just a constant line solution where the tangent line is 0 everywhere because the equation y equals 2, in this case, is a solution to this dE as well, right? Now, if I chose this as an initial point, it would start to flow down, and then it would kind of follow this solution curve of y equals 2, right? So it would be a decreasing curvature to this point and then go straight. If I were to drop a line here, a ball here, it would just flow down forever and ever, right? If I drop the ball here, it would go up and then it would curve to this line. So you can kind of see the flow of the different solutions starting at different points here, right? Okay, so a direction field, again, acts similar to modeling the current of a river. When we pick a starting point, we can then follow the point to trace the curve of the solution it would belong to, right? So again, as an example, let's say we looked at the point -3, 3, right? So I'm going -3, right, up to 3. So my curve here should then curve up, right? Okay. The solution to the curve would look like this, right? So if I'm starting here at this point, it's going to flow in this direction, right? And then the second half of this would be here. So it would go up, and then, like I said here, when x is 0, I'm always going to get a tangent line of 0. So we can't see what happens up the top because I didn't, zoom in that far. But it goes across. It is a continuous line. It's going to flow like this, right? It's going to be a quadratic looking type of function that has a limit of 2 as time goes to negative infinity, and a limit of 2 as you go towards infinity. Okay. So notice that the equation y equals 2 is a solution. This is called an equilibrium solution, right? As we said before. So now let's go over autonomous first order DE. So we'll talk about what an autonomous DE is as well. So an autonomous DE is basically a DE where the independent variable does not show up. Okay. So this DE that we have here is not autonomous because it has x in the equation, right? We're going back real quick besides the autonomous portion of this. If you notice, if y equals 2, I will always have a horizontal line here. So that's one way to see that that's an equilibrium point here, because it makes the slope 0 always. But this is, back to what I was saying though, this is not an autonomous equation because the independent variable is present in the equation itself, right? So an autonomous DE would be only in terms of y, or if it's a function of t and r of t or something, for instance, would only be a function of r. So whatever the independent variable is, it will not show up in the equation itself. Okay. In an autonomous DE, the equilibrium point is an equilibrium solution, right? So here, if I have any single point that is an equilibrium point, it corresponds to an equilibrium solution. That's not true in this case where I have a non-autonomous system, but in an autonomous system, that is true. Okay, so any equilibrium point is an equilibrium solution. Again, only in the autonomous DEs. That is not a true statement for something like this. That is not an autonomous DE, right? So let's do an example, or let's look at some examples. An example like this, where the independent variable does not show up, is an example of an autonomous equation, right? Y prime is square root of y. This is also nonlinear, by the way, right? Here, y prime is y squared plus y. This is also nonlinear. Okay, now it doesn't have to be nonlinear, but these cases it is, right? So these are autonomous because x does not show up in the equation. It being in the derivative notation does not count. This is basically y prime, right? It's not dy dx equals xy squared, right? X is not present here, right? So phase portraits, okay? So here's an image of a phase portrait. Phase portraits correspond to autonomous DEs. This is not true for the non-autonomous DEs, okay? So autonomous DEs have this relationship between its equilibrium solutions and sort of this this mapping onto the y-axis, right? This projection onto the y-axis. So if we have a critical point that represents an equilibrium solution, in between any two equilibrium points, there is a common direction of what the slopes are doing, right? Anything above a critical point has a common direction of what the slopes are doing, right? So in the regions between the critical points, the slopes all have similar characteristics, right? So in this case, this happens to be the critical point A over B. It doesn't matter what A and B are in this case. We could have just called this C, but I took this from our textbook, so it has actual values. But let's just say that this was a critical point, right? Call it C1. At this critical point, right, y equals C, it's always 0. It's always 0. But above it, I will be either always increasing or always decreasing in my slope. Same thing below it. I will always be increasing or always decreasing in between this region between critical points. Same thing here. If I had another critical point below, the region in between is always going to be always increasing or always decreasing. So what we do is we project to the y-axis, and we can draw arrows for what's always happening. Here, I'm always in a decreasing slope field. Here, I'm always in an increasing slope field. And here, I'm always in a decreasing slope field. So I can take this entire thing here, and I can turn it into a one-dimensional plot with arrows on it that tells me what's happening over this region of the number line, and this region of the number line, and this region of the number line. Okay. Now, let's go to the non-autonomous case, and we can clearly see that this is not the point. If this is my only critical point here, notice in the region above it, I have increasing and also decreasing slopes. Okay. In the region below this critical point, I have decreasing and increasing slopes. That's true because this is not a direction field that is associated with an autonomous system. Remember, this was with a non-autonomous equation. Okay, so if my system is autonomous, then I can draw this one-dimensional phase plane projection, okay, or phase portrait, I should say. Right. So here, I'll run through this real quickly, but it's really just reiterating what I said so that when you read these write-ups, you'll be like, oh, that's what's going on, right, when you refer to these later. So here we look at three different possible solutions to an autonomous DE bounded by the critical points C equals 0 and C equals AB. This just happens to be the form of this solution for this example from the book. The vertical line to the left, okay, here, acts as a representation of the projection of the slopes in the region the solutions to the DEs live on. So for instance, if I have a initial value that lies in between this region, okay, I will stay bounded in between that region, right? If I have an initial point here, any solution in this point will stay in this region as well, right? So they just kind of stay in their own lane, bounded by these critical points, okay, these equilibrium positions, okay. So in the upper region here in this example, all solutions are decreasing and they tend to go to this critical point as time goes to infinity, as my input goes to infinity, right? Similarly, in the middle, as I go to infinity, any solution that goes through any initial point in this region, right, in between 0 and a over b, will tend towards a over b as well, okay? And any solution that goes through an initial point in this region will tend to go to negative infinity, okay? So we call this a one-dimensional phase portrait, right? This line here. So let's go ahead and look at a slope field generator and let's play around with it a little bit. Okay, so before I get too crazy, let's go ahead and not show a solution, right? But let's look at how the different representations give us different pieces of information, right? So let's say I had a, let's keep this at 8, okay? Because you can see here we go up to 9, so I'll let this go up to 9. So we have a full field here. Okay. So here, my slope is equal to x. So whatever my x value is, that's going to be the slope. So obviously, as I go this way, the slope increases. As I go negative, the slope decreases. And that's for both regions. This is not autonomous, right? It's very clear that it's not autonomous because x shows up. In fact, my slope depends on x. But what I can do here is let's notice that the length of my lines, right, of my slope field vectors, give me different pieces of information, right? So if I make these a little bit longer, you can see that you can get a better idea for kind of what's going on here, right? Now, I'd say that's probably about standard, nice little size. Now, the density is very important, okay? Here I have it on the lowest density, and you can kind of see what's happening, but not really. But as you increase the density, the amount of slopes that you're projecting through the slope field, you can better and better see what the slopes look like, right? So if I have a large amount of slopes, they're very, very fine points in this case, right? But you can see sort of the pattern that develops here, right? So let's take this density down a little bit, right? You don't need a ton, but you can definitely see what's kind of going. You can see the flow pattern, right, as I like to call it. Right, so you don't need it super dense. Obviously, you can increase the size of the vectors that you're using. Okay, so you just kind of pick whatever makes the most sense for what you want to look at. Now, if you want to look at certain solutions, in this example, right, there's different slope field generators where you cannot show solutions based on initial condition. They only generate slope fields and they don't have conditions. But like, let's say, you know, as I move this around, you can see that the solution here is always x squared, right? And that makes sense because I have y prime equals x. So if you integrate this to solve, you're going to get 1/2 x squared plus c, right? So depending on where you want your solution to be, it's always going to be a parabola. Now, obviously, if we start to change things up, you know, my DEs look different, and then the solutions change based on the initial point, the initial condition that I want, right? If we, I don't think constant multiple is gonna, it's not ringing a constant multiple of those, right? So like, let's say I wanted to do x squared y, right? So now look at my slope field, right? It's a little bit different. It increases very quickly, right? And depending on my solution, right? So maybe you wouldn't have thought that that's what the solution looks like here. So what if we were to increase the density? Now you can easily see where if I were to drop a point in my field here, exactly where it would kind of go, right? Okay, so again, notice that it's not always, here it is always increasing and always decreasing, but that just happens to be for this case, because if I were to say minus y, for instance, right, now it's not autonomous. Notice there's no equilibrium point solutions, right? That's one equilibrium point, but it's not always increasing here. You see there's some decreasing portions. This is not an autonomous equation. It doesn't follow that phase portrait stuff that I was talking about, right? So once I start to get rid of my x, okay, now you can see these are all increasing portions in the numerator, okay, or in the quadrant 1 and quadrant 2. And down here, it's always decreasing. Now I have an autonomous system, right, with an equilibrium point of 0, 0. Okay, this is an equilibrium solution, and everything above this has a positive slope or negative slope, right? Positive slope, negative slope. Let's say I throw in a square here. Okay, now I have all negative, right? If I have an initial point here, it's always increasing. All of these are all going up. They're all going up. So I go from one equilibrium position solution until I have a function that goes through my chosen initial point, and then it comes to another equilibrium solution, right? So right now I have 0 and y equals 2 as equilibrium points, right? Those equilibrium solutions. Everything above has negative, right? What if I went minus 16? Right, let's put in quadratic. Say 7y plus 10. Okay, so here I have 2 equilibrium positions also, right? 1, 2, 3. Right, so here's an equilibrium, here's an equilibrium, and then maybe I increase this a little bit. Squared y, and then let's call this cubed. Okay, so now I have an equilibrium position here, okay, where everything above it has a positive slope, right? All functions are increasing. I have an equilibrium position at -2, and everything in between it has a negative slope. And then I have an equilibrium position at -5, where everything above it has a positive slope, and everything below it has a negative slope, right? So everything here is negative, and here is positive, negative, positive, and that just happens to be here. It doesn't always have to alternate in that fashion. Okay, but that's how these work. That's how the autonomous systems work. Once I throw in an X, for instance, it's no longer autonomous, and then as you can see, instead of having everything being positive here, I now have some portions where I have weird things going on, right? So once we are no longer strictly autonomous, we'll have some variations in what happens in our solution systems, right? As you can see, there's no more equilibrium points except for this one point here, but it no longer has the same sort of situation going on, right? The same sort of characteristics. Okay, so let's go ahead and go back to our lecture. I have some magic words I'd like to say. Abra. Now we're back into our lecture space magically. Wow, amazing. All right, so here we have what are called attractors and repellers. Okay, an attractor is a point like AB where we have something going up on one region, and on the opposite region, everything is coming down. So to this point, it's attracting everything, right? All the slopes go down to it from above, and all the slopes go up to it from the bottom, right? So it's an attractor point, or what we like to call a stable point, right? So here, everything is attracted to the C as long as our initial condition is somewhere around C, right? So we call that a stable point, okay? An equilibrium, like the other point that we had, C equals 0, is a repeller. Okay, this is a repeller because everything is going away from it, increasing away and decreasing away. Nothing is being attracted to this point here, right? So we have attractors or stable points and repellers, or what we call unstable points, right? So if I'm in this region close to C for initial condition, right, output wise, if my output is close to Y equals C, everything's going to go away from it. It will never attract towards C, right? And then if we have a mixture of the two, my critical point is both an attractor and a repellent, we call it semi-stable, right? It's both an attractor and a repeller, or you can say it's neither one of those. So it'll have some that come to it, and that's some that go away from it. So all of my my solutions, we're basically just going to go and they're going to pass through that equilibrium solution, right? So they're not going to stabilize there, and they're not going to go away. They're just going to pass through them, right? If it's above, it will pass down through past that equilibrium solution. In this case, if it starts off below, it'll go up above. If I'm already above, it'll probably never be equal to that point, right? So let's look at some examples. One more example, I should say. So this is an autonomous DE, right? There's no value of X in the equation. Basically, any zeros of these equations, of this equation, this portion, is going to be the critical point, right? Because any zeros here will make the derivative always a 0. So that's how you find out what the equilibrium points are. And then you just kind of look at points that are above it or below it, you know, to analyze your system to say, well, are things going away from it? Are things coming towards it? What about on the other side? Are things going away? Are things going towards? Then you can figure out, you know, is it a stable, unstable, or semi-stable sort of point, okay? Or you can graph it with the slope field, and then you can just look and be like, oh, this is a stable point or an unstable point. All right, so here, that's what I do. I graphed it. So let's say we hadn't graphed it. If I solve this system, right, if I put just this portion equal to 0, it's very clear that Y equals 0 is an equilibrium point, and Y equals positive 3 is an equilibrium point as well. So here you see Y equals 3 and see Y equals 0. Now, we might say, well, how do we know if it's an attractor or a repellent? Well, let's just pick a value above Y equals 3, right? So if I go, I don't know, let's say 0, 4, right, and I plug that in here, it's going to be positive or negative. Well, 16 minus 12 is positive, so everything above Y equals 3 should be increasing in value, okay, because that's how autonomous systems work. So let's pick a value then in between the other two critical points, the 0 and the 3, so let's choose 1. If I plug in 1, I'm going to get out a negative value, right, which tells me that everything between 0 and 3 is decreasing, so then above is increasing, below is decreasing. So y equals 3 should be a semi-stable point, right? It's not an attractor or a repeller. And if we go to our equation, or our field, that's what's happening. Everything's positive, everything is decreasing, so it's a repeller, right? And then if I want to look at the other equilibrium point, I just look at something below that, like -1. Well, -1 will give me out a positive value. So above is negative, decreasing, right? And then below y equals 0 is increasing. So y equals 0 should be an attractor. And it is, right? Everything is attracted to this equilibrium point. And this equilibrium solution, everything is repelled away. So that's how you would do that. I know I didn't write that all down, but that's just a quick analysis that you do in your head. Again, if not, you just go ahead and you plot the slope field, right? Use some sort of generator to do this, okay? Now you might be saying, Professor Williams, you're talking about all these generators, and where the hell do I find them? Well, if you're in my class, it's under the resources section in the Canvas module, under the welcome module. If you're not in my class and you want to know how to do this, you literally just have to Google direction field generator. There's a lot out there, but GeoGebra is the one that I like to use. So the one that I was using before is the GeoGebra site. Not to get too crazy with going back and forth here, but this is the site this is the full page that I was on, right? So GeoGebra, slope fields, I just did a quick Google search. GeoGebra has lots and lots of slope fields. People just come in here and they create them, and there's a lot of student generated GeoGebra sort of visualization tools, right? So I've never done this in my class, but there are other professors that, hey, as a project, I want you to create XYZ in GeoGebra. Okay, so going back to our lecture, this slope field that I did not create in GeoGebra is just some random offshoot site as I was trying to put this lecture together. But it did its job fairly well, although the numbers are hard to see, right? But again, here we can notice that the critical points are y equals 0 and y equals 3, right? And you can tell that just by looking at the graph, where you can take this f of xy function that's equal to the derivative, and just solve that for its zeros, right? So here y equals 3 is an unstable point, and y equals 0 is a stable point, right? An attractor and a repeller. Okay.